Good morning. This is the 6th lecture on X-ray crystallography and solid-state chemistry. We'll be talking on space group today. We have been discussing in lecture 4 and 5 point group as well as space group, how we derive a point group, how we derive a space group, and what are the importances of space group and point group. We have also discussed the stereographic projection of space point group with some examples of molecules. Now we are coming to space group. You know that for space group, we must have to know the point groups, and the 32 point groups, when we combine with Bryce lattice, we derive 230 space group. And we also know that the highest symmetry we get in cubic system, crystal system, the lowest symmetry we get in triclinic crystal system. Why I say that? I say that because we will see that it is very easy to describe a space group when there are number of symmetry is less and less and less. So in triclinic system, we have two space groups, only two space groups. One is P1, another is P bar 1. P bar 1. I could not make bar over there, bar 1. This is why I write P minus 1. But these two space group, one is enantiomorphic, another is centrosymmetric. Well, the lack of symmetry, other than one-fold or bar one-fold excesses in the triclinic space group, results a complete absence of symmetry constraint and on the unit cell parameters, as we discussed earlier. So, of these space group, if we take a few examples and explain them properly, then with this knowledge and some specific rules, one who are interested, they can consult themselves and learn more about space. So what we will discuss today, we'll discuss a few space group, how we represent it, and then talk about the specific rules and regulations, and then we leave this space group. Probably I will discuss 3 space groups. First one is number 1. It's called P1, and it is space group number 1. It is called mother of all space group. Why it is mother of all space group? Because all space group has that elemental symmetry. That is, it is one-fold rotation axis. One-fold rotation axis means that it complete 360 degree. Then you get the object you started with, the equivalent object again. So the mother of space group, and it possesses the symmetry elements of the space group. It is characterized by complete absence of any rotation axis other than identity rotation of axis of order 1. So we'll get only translation along A, B, and C unit cell direction, and then the symbol of these equivalent positions we write like this: T100, T010, and T001. This is what is a equivalent position for one space group 1. If we go for the next space group, you will say that we need to know some specific rules about how to explain space groups. So these rules are written in international tables for X-ray crystallography. Volume 1. And it is suggested that the new learner on space should see only the early edition of this international table of X-ray crystallography volume 1. The later editions will have some more relevant information, but then those informations are for specialist crystallographers. A common crystallographer or a usual crystallographer need not to know all those specialist rules and regulations. So what we do, this para will tell you how we explain a space group. A space group contains 2 to 4 characters. 2 to 4 characters. The first character is always the lattice type. If you remember, for 14 Barbized lattice, there are primitive lattice and non-primitive lattice. The first character is always for lattice type, and it is always written in capital letter. This P means primitive lattice, I means body-centered lattice, F means face-centered lattice, C side-centered lattice. These 3 are non-primitive, and this one is primitive. So, first character of a space group should be one of the Barbized lattice. In case of triclinic system, we know it does not have any lattices other than primitive lattice. We do not get any non-primitive lattices in triclinic system. That's what we discussed earlier. So this is the first letter, as we said, first character. We said the space group are between 2 to 4 characters. This is the first characters for triclinic system. And the remaining characters, what happens? We represent the symmetry elements that are present in the space group. We also discussed about point symmetry elements and space symmetry elements. So this is the remaining character are the symmetry elements that are present. Okay. Another rule is that if we have a unique or a principal axis of any crystal system, then the remaining 3 characters will be the specific unique axis symmetry elements. For example, tetragonal has got a 4-fold lattice, the fold axis, a specific one. And therefore, in tetragonal space group, after the lattice type, we write 4-fold, that is 4-fold rotation axis. Okay, the other characters will be depending on the rules of the crystal systems. We need not to bother about all those because this is not essential very much. That depends on which crystal system we are talking about. But if we do remember the first 2 things, that if it is if the first character is lattice type, and the next character of the space group should be one which is unique or principal axis symmetry elements, if there is any in the crystal system. Okay, we come to this para and we say that we represent this space group in a conventional way, that is, it's a parallelograms to represent the unit cell. So we take 2 parallelograms to represent the unit cell in the space group. And then we have also some convention. We fix the origin in the parallelograms in left-hand, top left-hand corner, top left-hand corner, what I show you here. And then it is in XY plane, as we are representing it. So y in horizontal way and the x in vertical way. That is what we represent a unit cell parallelogram. Then we have two of such. The right-handed one was the representation for symmetry elements, and the left-handed one are the representation of equivalent position. This is what the convention we have to remember this convention. The rule, this rule, and the convention to represent the space group. That we remember, and then we take one or two or three examples and then show that you discuss in the international table of crystallography volume 1, and you can understand all this. Okay. Now we take another space group. That is, this one is also triclinic, because we talked about triclinic P1, and we said we have another space group P. I showed it here as -1, but in fact we call it P bar 1. But you'll see that the bar over 1, and then it is P bar 1. So, though I'm sorry that I could not find the character bar 1 from the computer, and therefore I write it -1. In many books, it is taken -1, but it means that it is pronounced as bar 1, P bar 1. The second space group, we take the second number 2 space group is P bar 1. What happens? So we immediately say this is immediately, and the bar 1 means it has got a centrosymmetric point. Centrosymmetric point means you have a center of symmetry. So here in the left-hand diagram, we show the center of symmetry elements, only one symmetry, that is center of symmetry element. That's what we show. So this circle, this circle, this circle, this circle, this circle. This is how we represent the symmetry of the space group in the right-hand parallelogram. And this is the left-hand parallelogram where we are showing the coordinates of equivalent positions. Okay. That way, so we will see that this symmetry elements, that is center of symmetry element, is also present in the C faces. And what is C faces? C faces is bounded by A and B. If you remember the crystallographic axes A and B, the C faces is coming up A and B also. Additional center of symmetry we get in C faces. That here is an additional center of symmetry, which is not shown here. And all the other center of symmetry are created by the body center of the unit cell. Okay. In diagram B, what we are doing here now, we look for the equivalent positions. Well, to find the equivalent position, what we have to do, we have to choose a starting point. And what is starting point? We have to show where to start. And usually we start a starting point with a small values of X, Y, and Z. X, Y, and Z, small values of X and Y and Z. And these small values of X, Y, and Z would be from 0 to minus to 0 to 1. 0 to any value from 0 to 1. So this starting point, let's say we always start with a point very close to the origin. So here is our origin. As per convention, we start with this point. So next we find out which one is the equivalent position of this one after this center of symmetry element. And we will see that equivalent position, we go for this equivalent position, then start with this one, close to the origin, and all small values of x, y, z, what I said already, the position must be present in the other unit cell also. Do remember that we do not have only one unit cell. We say in our lectures that unit cell is the smallest unit of the three-dimensional lattice of crystal. So this smallest unit repeats three-dimensionally and gets the crystal lattices. And then if we have this one, equivalent position, due to the center of symmetry, we will say that this one is then coming up again in the next unit cell as bar 1. We say this is 1, and that what we call bar 1. Similarly, bar 2, 1 prime, and then 2 prime, and then 1, 3 prime. These are the this one position created after the center of symmetry elements in the next unit cells of this space group. Okay. Well, we have seen that here we have one last point here, negative point. This one is above the C-axis, or the plane of paper above, and this one below the plane of paper. And this comma means that this is an enantiomorphic notation. We come to this enantiomorphic notation later. Okay. After this, we'll go to the next slide and talk about little bit. Now, the effect of the center of symmetry at Q. We have a center of symmetry. This one, this is a center of symmetry. What happens that if we have a center of symmetry here, that this one will create another position where it is. It is below the plane of paper. So one creates 2 below the plane of paper. Similarly, due to this center, all other unit cell has got the all other unit cells got the all other unit cells got this 2 prime 2 and 2 prime 2 and 2 prime 3. So this is due to the center of symmetry. Okay, we show a center of symmetry here, how it relates the points. Well, we take example of 2 tetrahedra. Well, 2 tetrahedra positioned in such a way that they have a center of symmetry. Mind that individual tetrahedra will not have any center of symmetry, but 2 tetrahedra is positioned in such a way that, let's say, it has got a center of symmetry. They are at the equal position, the 4 corner of the tetrahedron. This is one corner, this is another corner, this is another corner, and this is another corner. When we have a center of symmetry, we create this 4 corner like this. So we can say this, if this is the right-handed system, this will be the left-handed system. So, okay. So you see, I now talking about enantiomorphic relationship. That effect, the inversion operation is to convert a left-handed object into a right-handed object or vice versa. That's what I explained here. Okay. Then we talk about this again. We have already finished it. Now we say that we have only 2 equivalent positions for this space group. 2 equivalent positions. What are the values? We say a value of x, y, z, and then 1 minus x, 1 minus y, 1 minus z. That is, if we take this one, and then this one will be 1 minus x, 1 minus y, 1 minus z. And that 1 minus x, 1 minus y, 1 minus z is represented by, it's called bar x, bar y, bar z. You see, this is how you see always in books, x, bar y, bar z. This means after a unit cell another X, another Y, another Z. So there is bar X, bar Y, bar Z. Though I have written here 1 minus X, 1 minus Y, 1 minus Z. That is after a unit cell, the next unit cell, the X minus Y minus Z, which is represented like this. So if this is understood, we go next to see a little bit more details about this. But we already said that bar 1, P bar 1 is the space group with number 2. It is number 2, and it has got 2 equivalent positions. And if one position is 1, we showed it, and the next position is 2 prime, and the coordinate is in the next position is bar X, bar Y, bar Z. That's what we have described already. Yeah, you see, this explanation is needed for understanding the space group a bit clearly. Therefore, it takes a little bit time. Today's lecture will finish here, and next lecture we start with these slides and explain more about space group P bar 1. Thank you very much.